we're going to learn about single replacement reactions, predicting, writing balanced chemical equations with them, as well as complete ionic and a microscale illustration showing a single replacement reaction. So let's go ahead and make sure you have all your items at hand. You'll need to have your periodic table just to remind you of the charges of your ions. You'll need to have your solubility to see what ionic compounds will be soluble and which ones will be insoluble. And then you're also going to need your activity series chart. And we're going to learn how to read the activity series chart. You're increasing in reactivity here, and then it's single replacement reactions only are used for activity series chart. Okay, so let's go ahead and get started on the example. The example is magnesium reacting with hydrochloric acid. By the way, you also should have your green sheet out so that you can practice your naming and make sure you have a list of strong acids so that we know which one dissociates completely and which ones don't. So, okay, let's begin. We start off with magnesium. So if you look at this reaction, you'll see that magnesium is on top starting off. And so it's Mg, and it's not magnesium ion. This is just purely magnesium because it just says magnesium, and it's not with another anion of any sort. So it's not an ionic compound. It's just a pure metal. Now we have hydrochloric acid. Hydrochloric acid is like this with two charges of ions, H plus and -1. Okay, and then the word solution suggests that this hydrochloric acid is going to be soluble and dissolve as ions in solution. So let's start off our reaction. We start off with magnesium. Magnesium reacts with hydrochloric acid, and it's in solution, so it's aqueous, and magnesium is a solid because it's a metal. Pure metals are solids at room temperature. And we're assuming all these reactions occur at room temperature. So what we're looking, if you look at this reaction, you can see that it's a single element with a compound, and that means it's a single replacement reaction. So magnesium is going to either replace the hydrogen or the chloride ion. But magnesium can only be a cation, so it has to replace the cation, which is the hydrogen ion. Notice it is positively charged. And so it's a single cationic replacement reaction. And so the next thing you want to do is look to see if it's possible to replace it. And this activity series chart will tell you whether it's possible. And what you're looking at is the two substances that will be substituting each other or replacing each other. And so it's magnesium and hydrogen. So I look at hydrogen and I look at magnesium. And I see that magnesium is more reactive than hydrogen. That means magnesium is going to probably bond more readily bond with chloride ion than the hydrogen. So it's going to kick the hydrogen out. In kicking the hydrogen out, magnesium now is bonded ionically with the chloride ion. So in kicking the hydrogen out, the magnesium is bonded with the chloride ion. So now we have to electrically neutralize that formula. So magnesium has a 2+ charge normally. Chloride ion has a -1 charge. So the formula is MgCl2. Then we go to the other product. The other product is hydrogen. Now recall that hydrogen would never be like this, hydrogen. It actually, nor would it be hydrogen ion. It actually will be hydrogen diatomically bonded to itself in what is called hydrogen, H2. So again, we're going to look at the states of matter of that, because states of matter are driving forces, whether it be a solid, liquid, or gas, or heat and light is also the other two, but states of matter are your driving forces. We're going to have to check out to see if we have any driving forces from the physical states. So the way we do that is we check our solubility table for ionic compounds. So since this is magnesium chloride is an ionic compound, I'm going to check my solubility table. And I notice that magnesium is right here, chloride is right here, and it's S, which means it's soluble, and so the designation is aqueous. So I'm going to put AQ. Now, hydrogen is not an ionic compound, so I cannot look on that chart, the solubility table chart. So instead, I look at the periodic table that Mrs. No has in her classroom, and I see that it's in red. And so those red means it's a gas at that temperature, which is about 25 degrees Celsius. So this is a gas at room temperature, hydrogen. And so now we're ready to balance this chemical equation. When we balance the chemical equation, we'll notice that we put a 2 coefficient here in order to balance the chloride ion as well as the hydrogen ion. And it looks like it well balances that, okay, both of them. And so we're left with this equation, which is simply balanced as a 1:1:1 ratio. And so we're ready for complete ionic. Complete ionic means we have to look at the physical states. That's why we put them in the first place. If it's aqueous, we can dissociate it. If it's solid, we leave it as a solid. If it's a gas, we leave it as a gas. So things that can be dissociated are your ionic compounds or your acids that are aqueous, okay? Acids or ionic. So let's go ahead and leave magnesium as is. Dissociate this because it's aqueous. And it's a strong acid. Now, how do you know if it's a strong acid or not, or whether it is or not? You look in your green sheet. If you can pause this video and find the chart that says strong acids. Strong acids will completely dissociate. Weak acids partially dissociate. And 100% of the time, strong acids will dissociate. Only 10% of the time, weak acids will dissociate. So that's why it's important to look at your acids and the chart on your green naming formula sheet, okay? So now we look at this substance, and it looks like it's aqueous, so you're going to dissociate into ions. So notice the ions that are formed as a result of the dissociation of magnesium chloride. Now we go to H2. Don't dissociate because it's a gas. Now I'm ready to cancel out my spectator ions. Now, again, when I look at spectator ions, I'm looking to see if they look exactly alike. My spectator ions should look identical. Do these two look identical? Although they're both magnesium, one has a neutral charge, a 0 charge, and the other one is +2. So one looks like this, and the other one is +2. So they're not identical. Likewise, this is H+ ion, and this is just neutral H2. Okay, so let's look at chloride. Oh, those two look identical, so they are our spectator ions. So what we're left here is magnesium neutral, that's a solid, plus 2H+ aqueous ion, yields Mg 2+ aqueous, and H2 gas. So the question that you're asking is, what's the driving force? Well, production of a gas is always a driving force. So this is definitely a driving force that we will notice, observable driving force that we will notice. Now, then you're going, what's happening in this reaction for your chemical change? Notice how magnesium is neutral here, and then it becomes a 2+. That means magnesium lost 2 electrons. Well, who do you think gained those 2 electrons? Each of the hydrogen ion will gain an electron. Upon gaining 1 electron, each ion, it now becomes H2 neutral. And so that's why you see elemental hydrogen from the hydrogen ion. So that's the underlying, what's happening underneath the surface of that reaction. So let's go ahead and represent reactant 1 and reactant 2. Now this is reactant 1, this is reactant 2. So magnesium is a solid. Notice it's a metal, so I'm going to leave it as a solid on the bottom of this beaker. And then hydrochloric acid is a solution, and so that solution is going to look like this with 2 hydrogen ions and 2 chloride ions. Now we go to the product. The product, we're still in solution. You're basically dropping this piece of magnesium into the solution of hydrochloric acid. And so we're still in solution. And because we're still in solution, we have the presented ions right here. There's magnesium 2+. Reminder, I'm looking at the complete ionic, so I know what to put into my solution. Now, something different from double replacement. In this reaction, you're forming H2 gas. So in H2 gas, you're going to see it released as a gas. So it's going to be above the liquid. And you're going to see it released out into solution, okay? Out of the solution. And that here, class, is the microscale illustration. If you have any questions, let me know.